Now sometimes we are more interested in heat transfer in a particular shape, so conductive heat transfer from very common situations. In that case, our job is actually very easy if the geometry we have can be approximated by some of the cases that we have in the book. Now, the equation is that the conductive heat transfer rate equals the shape factor, which is defined for all these cases. You can see equations there for all 8 of these, times the thermal conductivity of the conducting medium. So let's take case 1 for example. If that was a pipe buried under dirt, then K would be the thermal conductivity of the dirt, which is shown as just a bunch of dotted crosshatch, times the temperature difference between whatever shape we have versus some other temperature of some other point. In the first case, it's kind of like a pipe buried underground, and the surface then would be the surface temperature of the ground, T2. But we could talk about heat transfer between 2 bodies that are buried, like in case 3, and so on. There's plenty of examples here. So our equation is actually very simple. All we have to do is be able to use these shape factors. Now, one thing you need to be able to do is use the hyperbolic functions and the inverse hyperbolic functions. I do not expect you to be able to calculate these by hands, but you desperately need to grab your calculator now, pause the video, find an instruction manual on it, and figure out how to use the hyperbolic functions. And notice there's, in case 3, a hyperbolic cosine inverse function that you need to know where that button is on your calculator. I think on some TI calculators you have to go into library. Others, especially most scientific calculators, it's just a few button presses with shifts and things. But you need to know where that's at. Of course, there's natural log here as well. It's used several times. And some of the shape factors are simple, like in case 8, it's A over L. That's a really simple shape factor. There is another page of these, so we've got 16 different common configurations where we can calculate heat transfer rates in very common shapes. Now, I need you to notice something. You need to make a change in your book. Every book I've ever seen of this edition has an error in case 10. It's on page 430, and notice that the A and the B are flip-flopped. So I have fixed it in a graphics program, so this slide is correct. Make sure that your book matches this slide for case 10. And like I said, it's usually just a flip-flop of dimension A and B. But if you make them just like I've got it here, you'll be fine.